Okay, so I'm going to pick up where we left off. And if you recall, we were talking at the end about the Euler characteristic. And what I'm going to do today is talk about, finish talking about K0, which basically amounts to a very brief précis of the wall finiteness obstruction, or an assertion of the existence of the wall finiteness obstruction more than anything else, as you'll see. And then I want to talk about K1. And K1 is another kind of K-theoretic invariant, and I'll say a little bit about why K1 should be thought of as related to K0. And today is kind of the last part of the review of what you might think of as classical algebraic K-theory. And we'll then, tomorrow, I guess, radically shift gears and move in the direction of modern homotopical algebraic K-theory. I will try to make that transition as unnauseating as possible. But anyway, let me get started with the Euler characteristic. So the general setup that we have, and we're going to see categories of complexes in more detail, and so I'm not going to say an enormous amount now, but if we have R as our ring, then we can think of the category of complexes in R mod. And the objects here, so what are the objects? I'm going to think of them as sequences, which I'll often write as something like M dot. And these are integer index sequences, mi to mi minus 1, and so on, where the mi is an object in R mod. And we have these maps, these differentials, and these have the property that di compose di minus 1 equals 0. Okay? These are the objects, and the morphisms are what you think they are, namely they're the commutative diagrams. So they're some morphisms. A morphism, I write this here. So a morphism from M dot to M dot is a collection of maps Fi from Mi to Ni, which are R module maps, and I require that all the diagrams of this form commute. And another way of saying this, maybe I should label that's Fi, and that's Fi minus 1, and so on. Another way of saying this, incidentally, that makes the functoriality clear, and is sort of, this is not maybe the world's most useful perspective for chain complexes, but as a sort of life philosophy, it's good to start seeing things like this. You can think of these as diagrams. This is a functor from Z. Any partially ordered set is a category, right? And this is a functor from Z to R mod, along with some additional structure encoding the fact that we want the composite of this to be 0. So it's a subcategory of that category. But this tells you immediately it's functors like this. Natural transformations are the morphisms, and if you unpack, this is what a natural transformation is. Okay? So functors like this, and morphisms are natural. Okay, so that's the category of complexes, and the most important thing we can do with a complex, well, one of the most important constructions on a complex is its homology, right? You know this, right? The example you should keep in your head, right? What's the example? And the one that's particularly relevant for the classical applications of the Euler characteristic is the cellular complex of a CW complex, right? Now, as we'll see, or maybe as you remember immediately, that complex has special properties, right? That's not just any old complex of R modules, it's a complex of free R modules, which might bring us back into mind of K-theory. You might think about complexes of projective R modules, and we'll specialize in a second. But anyway, so we have a complex, and of course, for any complex, well, let's write it like this. We can define, of course, the homology of Mi. And what that is, remember, that's just the kernel of di mod the image of di plus 1. And this constraint, I guess there, or sorry, I shouldn't point randomly, that constraint tells us that this actually is meaningful, right? OK, so we have the homology. And one definition I want to make further is we'll say that a map F between complexes is a quasi-isomorphism in the event that, if what I might write is hf from h dot of m to h dot of m is an isomorphism. OK? And this notion of quasi-isomorphism, this is going to recur for us because we're going to be moving, and I said something about this, a little bit about this last lecture, and I'll say a lot more about it tomorrow. We're moving away from setups where isomorphisms are right. When you work in topology, it's I mean, some people do, but it's relatively rare to want to classify things up to homeomorphism, mostly because we can't in any sort of interesting examples. Where we work is up to homotopy equivalence, or weak equivalence, and in the algebraic setting, what you might want to work is up to quasi-isomorphism. And so, we saw an example with finite CW complexes of generalizing the definition of K0 in this direction, and there'll be more of that. OK, so now for any complex, well, let's make the following definition, actually. So now if M is a bounded complex of finitely generated projective R modules. So bounded here just means that most of the terms in these things are 0. OK? So, and again, the example is if you have a finite CW complex, the cellular complex is, is 0 except in the range between the dimension, or up to the dimension of the complex. If we have such a thing, I'm going to define the Euler characteristic, and that should be a chi, of M. This is going to be a class in K0 of R. OK, so we want, this is another kind of reason, or another way of seeing this slogan that K theory is about providing a home for Euler characteristics. Rather than having numbers, we're going to have this live in K0 of R. And what is it? It's going to be, and, what's the formula? We'll have chi of M is equal to the alternating sum. Maybe I shouldn't write it like that, or certainly not starting at 1. Right? It's the alternating sum of the classes in K0 of the constituents of the complex. OK? Now, one thing you note, so that's a nice definition. One thing you observe that I mentioned last time, but I'll say again, is that, make an observation, which is that the Euler characteristic of M is equal to the Euler characteristic of H star of M. Now, how am I regarding, to fit this into the same context, how am I regarding homology as a complex? Well, I'm just imagining I have the 0 differential. Right? Certainly a perfectly good complex is the one where the maps connecting your modules are the 0 map. And part of the point of why the Euler characteristic is easy and cohomology is hard is that, or harder, is that the Euler characteristic forgets about the attaching maps, right? It's just a cell counting device. And so, that's sort of why this might be plausible. So let me say a little bit about how you prove this. Let's imagine, let me sort of specialize to the setting of vector spaces, but this proof more or less works anywhere. So actually, let me write one thing. So why would we care about this? What this tells us, right? What does this say? The consequence of this is that the Euler characteristic is a quasi-isomorphism invariant, right? It says that, yeah?
So if you take the homology, you may not end up being projected.
Yes. So, yeah, I think I will actually, won't I? There's not going to be a wedge sum end of the free thing you start. If I started with something free, I think that I will.
But if you take a general complex of projectors and take the homology of it,
No. Yeah, no, you're right. Let's interpret this in a setting where it makes sense. So, yeah, that's, goodness, what do I actually want to say about that? Yeah, you raise a good point. Let's restrict to the case where we're working over a field, in which case then everything is going to be easier. So there's something correct to say in general, which I am losing right now, but let's restrict to working over a field. So let's restrict to a field. Then how do you know, what's the way to see something like this? Well, you know, goodness, this is really a mess. What do I actually want to prove? So this is, right, okay. So I gave you here the K0 version of this. I can do the following sort of thing. Right, there's the classical version, right? We're used to, so here Euler characteristic is a K0 class, but classically Euler characteristic is a number. And there the formula is that, you know, the Euler characteristic of M star equals the alternating sum of the rank of the module. And so let me explain, and so what I want to explain is a counting argument that tells you why, in this case, this is the same thing as the Euler characteristic from -1 to I of the rank of h of mi, at least when we're working, and again, I'll explain the proof. Now we're going to work with R, a field. And indeed, something like this is true in the K0 setting, but let me get that straight and tell you what the right thing is. Anyway, so how do you see this? Right, well, the point is that, remember that in this particular case, you know, mi is splits up as the kernel of di plus the image of di, right, or sorry, the rank of mi, rather, is equal to the rank of the kernel of di plus the rank of the image of di. Right? This is linear algebra. On the other hand, the rank of hi of m is equal to the rank, that's a quotient, and in this case, the ranks is just going to be a difference. Right? So this is equal to the rank of the kernel of di minus the rank of the image of di plus 1. Okay, and now, how does this proof work? Well, if you unpack both of these sums telescope, right? So the thing you say now, and this is something nice to write out for yourself as a very small exercise, is that the sums telescope. Okay? And this argument, it turns out, you can, so I'll say something sort of precise about abelian categories slightly later in this lecture. And this argument, in fact, can be made to work in that setting. But in any event, okay. So what do I want to do with the Euler characteristic? I now want to think about the wall finiteness obstruction. And the setup here is the following. So we'd like to know, again, this is related to the problem of classification of compact manifolds. And as discussed a little bit last time, we know for various reasons that M is homotopy equivalent to a finite CW complex. Now we also know, and again, you can see this from if you have an explicit triangulation. So if you're working in the PL category, this is very easy. If you're working for in the smooth category also, if you're working in the topological category, this is very hard. So this ranges from an exercise that you should do, at least if you know something about triangulations on manifolds, to an exercise that if you did it, that would be an achievement to be extremely proud of, although it is a known result. Okay. So we also know that in general, we can embed M in some very large Euclidean space. And what this turns out to mean, using the theory of Euclidean neighborhood retracts, is this implies that M is a retract of a finite CW complex. This is not obvious. You have to know something about the topology of what are called Euclidean neighborhood retracts to prove this. But it's true. And it motivates the following question. Suppose that I have a setup like this. I have X, and I have some bigger ambient space Z. And I have the following diagram, where this is the identity on X, and this diagram homotopy commutes. Okay, so it doesn't actually need to commute, but it commutes in the homotopy category. Then what I'm saying here is that what this data says is that, a succinct way of saying this is that X is a retract of Z in the homotopy category of spaces. Okay? So now let's imagine that what do we want to imagine? So let's imagine that Z is a finite CW complex. I should say that there's a nice related but much easier exercise about this kind of domination situation in Peter May's textbook on algebraic topology. So if you want to see at least one problem about it other than what I'm going to tell you, you can look there. But Z is a finite CW complex. Then we can ask the question, is X, at least of the homotopy type, of a finite CW complex? It's relatively straightforward using this exercise in Peter's book to show that if Z is a CW complex, or the homotopy type of a CW complex, then so is X. The rub here is this finiteness. And the answer to this takes some work to set up, but the story is something like the following. So let's imagine now we take the universal cover of X. Now, if we think about the cellular complex of X tilde, so this is the cellular complex I am asking a question. Yeah, so I guess I'm writing in this way where you can't tell whether that's a question or an assertion. Let me decorate. Right, so the setup is, I apologize. Let me try to be clearer. The setup is you have a diagram like this. I tell you that Z is a finite CW complex. When is X a finite CW complex? Can you give me a criterion, an effective criterion for deciding when X is a CW is a finite CW complex, or of the homotopy type? So, right. So we have this universal cover, and what you observe about X tilde, so a straightforward observation, is that this is a complex of Z pi 1 of X modules, right? These are modules, in fact, over the group ring on the fundamental group of X, right? And this just comes from covering space theory, right? The pi 1 of X acts on the cells of X kind of over each point of X, or each cell of X. Now, that's an easy thing to check. What's not so easy, but is true, is the following, which is that, in fact, C star of X tilde is quasi-isomorphic to a bounded complex of finitely generated projective Z pi 1x modules. And this takes some work to show. This is work I'm not going to do, but there are many good treatments of this. I mean, Wall's original paper is actually very readable. If you are interested in this sort of thing, I highly recommend it. But one proves that, in fact, this is isomorphic to a bounded complex of finitely generated projective Z pi 1 modules. And what it turns out is that the next thing you show is that X is finite if C star X is quasi-isomorphic to a bounded complex of free Z pi 1x modules. Okay? This again requires proof, but is true. An exercise you can do, if you're interested in this, that's sort of more approachable, is to say if X is a finite complex, to show that the chains on X tilde is a complex of free modules. That's a relatively doable exercise. So now if you have this, so what we're asking for is we would like an, yeah.
Sorry, we're just not talking about C star X.
Thank you. This is true. I think I want everything to have, let's see, what do I need for that hypothesis to be true? Yeah, there are some niceness hypotheses on pi 1, for instance, that you need, I think, in order for this to work out. But I don't remember precisely, so let me defer that.
Are you giving yourself that X is a CW complex?
Well, we know that, so if Z is a finite CW complex, I'm sorry?
So I thought you were answering the question when it's finite CW complex.
Right, and so what I'm about to say is that if Z is a CW complex, finite or not, then it's an easy exercise. Comparative, none of these exercises are that easy. So I apologize. I use the phrase easy exercise, and easy here often means something like not insanely difficult, or you know, like you could solve it if you did nothing else for the next 4 days and had some background. Not, you know, you should feel bad if you don't see this by the end of the lecture, right? But it is an exercise that is suitable for an introductory graduate course in algebraic topology to show that if Z is a CW complex, forget the finiteness, then X is of the homotopy type of a CW complex. So we can assume that X is a CW complex. What we can't, or at least of a homotopy type of one, the question is whether or not it's a finite CW complex. Yes, I'm sorry. Yes, I want to assume that. Thank you. Yeah. So, okay. Any further questions on the setup of where we are? Okay. So we have this. So we want an obstruction to being a bounded complex of free Z pi 1 x modules. So the point is that that's a question that K0 can answer, right? If we think about, so the claim is that if I take chi of, you know, this thing, right? This is a class in K0 of Z pi 1x, okay, by previous discussion. And it's actually a class, so remember, there's always a map from Z into K0 of R. This is just a map that takes an integer to a free module of that rank, or its formal difference, right? If you're, you know, its formal inverse if you're using negatives. And so we can be interested in the co-kernel of this, which we might write as K0 tilde of R, right? So we're going to ignore the things that came from free things. So the question is sort of what's left. And in some sense, we're ignoring, you know, formal differences of free things. And so we can regard, in fact, this invariant as living in here. And the question is now, is that invariant 0 in this group? So let's call this, let's give this a name and call this W of x. And if Wx is 0 in K0 tilde Z pi 1 of x, then x is finite. And that's, in fact, an if and only if. OK? So this is, I mean, unfortunately, as is apparent, I'm not proving much of anything. I am telling you a story where you would need to actually do some work to turn this into something resembling actual mathematics. Nonetheless, the point of this story, I mean, this is actual mathematics, but I just made a bunch of assertions. The point of this story is that K0 is the home for an invariant which is answering what's really a purely geometric question, reduced to a question about a certain ring. And this kind of construction, so I'll say this now, we have a bunch of different sorts of examples. What sorts of examples do we have? Right, we can think of sort of K0 of R, where R is a Dedekind domain. And this is, you know, this is sort of a number theoretic example. But we can also think of K0 of Z of pi 1 of x. And this now is telling us somehow about manifold geometry. Okay, so this is, right, the program, as always in algebraic topology, is turn questions about geometry and topology into questions about algebra, because notionally algebra is easier. I mean, algebra might still be really hard, but it's often easier than the geometric arguments. Now, one suggestive thing to say about this is this should remind you, this is very closely related, or this is a shadow of a construction that came up in Mark's talk, which is when you see this, what you really might want to think is something like this. And you know, you might wonder, how do I really make sense of the group ring on the loop space? And the answer is, well, what you probably really mean, maybe, is something like this. Namely, the suspension spectrum of the loop space with a disjoint base point. This is an example of a ring spectrum. And where we are going is that we want to be able to put ring spectra into K-theory as a massive generalization of this kind of construction. And in fact, it's the case that if I take the K-theory of this ring spectrum, what I get is an invariant that is related to the diffeomorphism group of a manifold, at least if you're in high dimensions. Well, I say we'll see. What I really mean is I'll tell you how to construct that thing, and then I'll assert it's related to manifold geometry, but that's sort of like us seeing. So anyway, the point here is that broadening the input of K-theory widely allows us to capture a lot of stuff. And I haven't even written down the examples that are things like K-theory of finite G-sets, which is closely related to the structure of the stable equivariant homotopy category. Okay? So, and I think that's possibly ends my treatment of K0 for the time being. Let's find out if I had anything else I wish to say about this. No. Okay, so now we move on to K1. Right, where are we going to go next? Right, so okay, so we now turn to K1. So where does K1 come from? Well, where did K0 come from? Right, what was the strategy? Our general move was we wanted to study, so recall that we wanted to study proj R, and so we looked at isomorphism classes of objects. Right? K0 is the sort of the minimal algebraic thing you make out of isomorphism classes of objects. Right? It's solving a classification problem. It's kind of magic that it actually encodes as much as it does, right? But that's the world we live in. Now, if you were slightly more sophisticated, you might think, if I want to understand a classification question, it's not enough to understand just the isomorphism classes of the object. Maybe I want to understand their automorphisms, right? Symmetries are a very natural thing to ask. If I have an object, what kind, and I want to know about it, what kinds of symmetries does it have? So, you know, it's very, you know, we might, so more sophisticated, ask about symmetries of objects. Okay, so what does that mean? That means I might be interested in what I might write as the automorphisms of M, and these are the invertible maps from M to itself, right? The self-isomorphisms of M. Now you notice that this already has an algebraic structure from composition, right? This forms a monoid under composition already. Now, we know some examples of this. Or let me give you an easy example. So supposing that I'm looking at maps from Rn to Rn, okay, where here R is a ring, any old ring. So, I mean, you know this, right? What are the maps from Rn to Rn? They're matrices, right? This is the same thing as matrices in R. And if I want those matrices to be invertible in order to get the automorphisms, then, you know, aught Rn, which is contained in the matrices, is equal to GLN of R. Right? So as soon as you go in this direction and you think algebraically, matrix groups arise, mostly because we've restricted our attention to either free things or things that are wedge summands of free things. Right? And I'm going to make, well, I'll say something more about the distinction between free and projective in this context in a second. But so you might expect that GLNR is going to come into any kind of invariant we make in this direction, and indeed it does. So I'm sorry? Yeah. So remember, direct sum is the coproduct and the product. So it is strictly correct, although perhaps misleading, to refer to it as a wedge summand. But right? I just mean that the coproduct splits off. And maybe I should say as a point of reference, so the reason I say that is that in an additive category, as we'll see in a little bit, or as I'll assert in a little bit, products and coproducts are the same. In the category of complexes, this is not true. Or in the category of spectra, in fact, I think both Mike and maybe Brooke and maybe Mark have all mentioned that the coproduct and the Cartesian product are equivalent, but they're not equal. And it turns out to be correct to think about the analog of projective as splitting off a coproduct rather than a product. Hence the terminology. Okay, so, right. So one thing we can do, so what do we want to do out of this? We want to make an abelian group, right? Always we want to end with abelian groups. So how do we get an abelian group out of GLN of R? Well, I have a map, very natural map from GLN of R to GLN plus 1 of R. And what do? I just take my matrix, M, and I insert it into a bigger matrix, where now I put a 1 in the bottom. Right? And this is a very natural inclusion. And I can take the colimit, or the union over this, and I can define GL of R equals the colimit over N of GLN of R. And great, so now I'm thinking about sort of infinite dimensional matrices, or matrices of unbounded dimension, but any particular one sort of came from someplace finite. Right? That's what this means. And again, if you're not comfortable with colimit, think of this as a union. Okay? Now, this is not abelian, but that's no problem. We will, whenever we have problems, right, we use a universal construction to make things what we want. So what are you going to do? Well, let's take the abelianization. Right? So one thing we could do is we could look at GLR abelianized. And what is that? That's GLR mod the commutators. Right? That's a perfectly reasonable thing to do. Now, so we could define a provisional definition. I shouldn't say provisional. A really great definition is that K1 of R is equal to GL R abelianized. Okay? And that's an abelian group. Now, there's some things about this that are a little bit unattractive. There's some things about this that are fabulous, right? I mean, one of the stories here is that algebraic K-theory of rings is about linear algebra. And, good God, this should look like linear algebra. And it's going to look even more like linear algebra when I identify what the commutators are. They turn out to be related to Gaussian elimination. So, it's really going to be linear algebra. On the other hand, there's some unattractive features of this definition. So, two things that might worry you about this. One, what happened to the projectives, right? These are the automorphisms of the free modules. And you might wonder, where do the projectives go in this setup? That's a reasonable question to ask. The answer is they were absorbed, as we'll see, but you got to worry about that. Two, and this maybe is a sharper objection. One of the attractive things about K0 was that K0 takes in a very wide array of input. Now this, as it's constructed, does not. Right? If I just give you some random category with exact sequences, it's not very clear how to make that into, how to make a K1 of this form out of that. Right? So two, what about general categorical input? So fortunately, we can resolve both of these issues simultaneously. And I'm going to give you another definition now of K1 and explain why it's the same. So what is this other definition? Well, if I have a category C, then I can form, so C, maybe I should say, is a category. One thing that I've been careless about, incidentally, and I'll mention this carelessness now and then return to being careless about it, is that in order for these constructions to make sense, inevitably my category has to be small, right? I've always been acting like I have a set of objects, or at least a set of isomorphism classes of objects. And so I'm tacitly assuming that basically everywhere. This isn't a bad assumption because the Eilenberg swindle tells you you really need to be really quite small in order to expect non-trivial invariance. But this is lurking in most of what I've been saying. OK, so C is a small category. Now I can form a category I'm going to call ought C. And what is this? Well, the objects are what are the objects? The objects are a pair x gamma, where x is an object of C, and gamma from x to x is an automorphism. Right? Very natural thing to do. I'm now keeping the data of a module and a class, a free module, for instance, and a matrix, if you want to think about it that way. And what are the maps? Well, the maps are sort of what you might hope. Namely, if I have x to y, and I have, here's gamma, and here's gamma prime, then the maps are maps F that make this diagram commute. Okay, this is a map from x gamma to y gamma prime. Okay? So now I have this category, and now I'm going to make the following definition. So I'll say two things about this construction. Well, I'll say a bunch of things about this construction, but let me start by saying two salient ones. OK, so two observations to make. One, if C was symmetric monoidal, so is ought C, right? Add the modules, add the automorphisms. OK? So we have x gamma, we have y gamma prime, now we have x plus y gamma plus gamma prime. So we inherit the structure of possession of the symmetric monoidal product. Two, if C has exact sequences, whatever we might mean by that. Remember, we've talked in a setting where I just have a distinguished class of sequences that is closed under isomorphism. It might have other properties, but right now it's just some class of sequences. If we have C has exact sequences, then ought C does too. And we define them via the forgetful functor. So what do I mean by define them by the forgetful functor? Well, I'm going to say that a sequence x to y to z to x, y, z, and here's gamma 1 and gamma 2 and gamma 3. And this is exact if x to y to z is exact. OK? So, I'm sorry? Yeah, I mean, that's a diagram in the category. So the diagram commutes. Yes, that's right. Thank you. So if we have maps in the category, if we have a diagram like this in ought C, it's exact if the underlying diagram on objects, where we've forgotten the automorphisms, if that is an exact sequence. So this is an interesting thing because let's make a few more observations. Now, let's think now about proj R. We recall that if we use the structure of exact sequences, the usual notion of short exact sequence in proj R, right, coming from ultimately the abelian category structure on mod R, then recall that all short exact sequences split. So there's no difference between the direct sum version of K0 and the exact sequence version of K0 in this context. But if we look at the automorphisms of Proj R, then it's not the case anymore that all exact sequences split. This is no longer true. And it's a good exercise, think about what it means for an exact sequence to split. So if you think about splittings in this context, what you're talking about is a 2-by-2 matrix, right? And there are conditions on that matrix that correspond to the diagram splitting, right? What I mean is that, if I had X with its automorphism, to save time, I'm going to draw it with these little self arrows, but I mean, something like this. If I think about something like this, then on a splitting, a map from x plus z to x plus z is some sort of 2-by-2 matrix about x going to x and x going to z and z going to x and z going to z. And in order for this thing to be to arise from a splitting, this matrix has to have a certain form. So the exercise is to figure out what form does that matrix need to have. This is a nice exercise. So when do exact sequences now, another thing I might say about all of this is that we can give, I will actually eventually define K1 again, but let me say first that I can give an algebraic interpretation of this automorphism construction. So if we think about what of Proj R, this is the same thing as Z write that properly, RZ modules that are projective as R modules, right? The Z action is the action of the automorphism map. That's how this thing acts on such a module, right? The R part acts because it's an R module, and the Z part acts, the generator is the automorphism, and if you want to act by 50, you do the automorphism 50 times, okay? And then the automorphism has an inverse, so it's Z and not N. If you were thinking about endomorphisms, this would be N. Now, what's weird about this from an algebraic standpoint? So this is a tricky theory to work with. And one of the things that makes it tricky is that these are basically never projective as R adjoins Z modules, right? It's a very weird algebraic thing because they're the projective, the smallness condition is coming from the forgetful functor. And so that makes it hard to think about these algebraically, but it's sometimes illuminating nonetheless. Okay, so I now want to return to my definition. So K1 of C is going to be equal to K0 of the automorphisms of C. Okay? So this is a definition. This definition has some appealing features, namely, well, it's categorical, and it's in terms of K0, which are things maybe we feel like we understand a little bit now. Let me make an observation. So what's the observation that I want to make at this point? Right, where are we? So let's say proposition that K1, well, in order to justify writing what I wrote, I need this proposition, which says that K0 of the automorphisms of Proj R is isomorphic to the abelianization. Okay, that's how you interpret Or that's how you go between these two different depictions of K1. How do you see this? Well, you see this by constructing maps back and forth. And these maps are, surprise, surprise. And these maps you can describe in terms of universal properties. Remember, almost everything we're doing here, there are various universal properties at work. And so you don't have to give very much data or check very much to give a map, right? You just have to check that you have sort of a map on objects which is compatible with certain of these relations, right? Which we know. So, you know, what are the maps? So we want maps back and forth. And I should say, sort of as a slogan, these are going to come from the universal properties and what they have to be. Let me do something easier first, which is so, you know, easier thing to check is that K0 of aught of maybe what I'll write as free R. So this is finitely generated free R modules. That this is isomorphic to GLR abelianized. Now, before I explain a little bit about the proof of this, let me point out that there's something interesting going on which didn't happen with K0. Right? We have, put this in a marginal note, we have what gets called a cofinality phenomenon, or just we have cofinality, which is that free modules and projective modules are closely related. Every projective module splits off a free module. And it turns out that higher K-theory invariants are insensitive to that distinction. That what we're saying here is that sort of, you know, K1 of frees and K1 of projectives is the same on the left side of this. This does not happen for K0, right? All of the interesting applications of K0 are precisely when projective and free are different. But K0 is the only place that you feel that. And I'll say more about what's going on with that a little bit later. But, you know, K1 can't distinguish proj R and free R, even though K0 could. Okay, so how do we do this? Well, let's explain how to write this down. Okay, so let's make some maps. Let's give a map from GLR abelianized to K0 aught free R. So, I mean, the map is what it has to be, right? You don't have a lot of options here. So what does something in here look like? It looks like a matrix. Right? Remember, what these infinite unions look like is that there's no global bound on how big the matrix can be, but at some point it starts being all ones. And that's a finite point. So let's just cut off that piece. So, you know, a representative of something in here is just, let's call it A in GLN of R. That represents some generic element. Right, and we've of course done things. So there's an equivalence class of such things, but I'm going to pick a representative. And now what do I do with that? Well, what else could I do with that? That's an automorphism of Rn. So I take this to the class of Rn, comma, A. Okay? And, you know, you have to, so what I'm going to write down is this is a map sort of on objects, and what you check is that this is compatible with the definition here, right? So you have to check that this actually defines, check that this induces a map. I should say, really, this induces a group homomorphism. Okay? And that's an exercise. This is a very doable exercise. How do you go back? Well, if you want to go back, it's the same thing, right? If I'm on the right side of this equivalence, if I have a class in the automorphisms of the free modules, what is that? That's an Rn and an automorphism. That automorphism is a matrix. You bring it back. Now again, you have to check using the universal property that that assignment on objects actually induces a map, right? It has to be compatible with the relations imposed here, but it is. And so, I mean, but you check, and that's it. So, the inverse map is, again, the obvious thing. And it's an exercise. Check. These descend. Now, I want to highlight that this argument, this sketch of an argument, highlights why it's so useful to have universal characterizations of these constructions. Right? If you do this anyway, you will feel this. I wrote down maps on objects that were, and sort of on representatives of objects in a very loose way. But it turns out that it's because of the universal properties of these things, these are actually forced to be group maps, which is great. And for using the universal properties, you can check. Okay. So the last thing I want to do in this direction, in terms of this definitional business, is comment a little bit further on this business about the difference between projectives and frees. And the point is that, you'll notice that if I look at this construction, so I built, recall that GLR was equal to the colimit of the automorphisms of Rn. Right? That's what that was. Now, in general, if I can do this construction, so I lied a little bit. I made this assertion that, this really mostly makes sense for, for rings, and we have a problem extending this to categories. But really, you can extend this to categories, right? What do? I can, in general, for any C with a symmetric monoidal product, I could play a game, right, where I look at some sort of colimit over the automorphisms of X, where X is an object in C. And in order to make sense of this, so here I told you what the maps were along which I was taking the colimit, right? I told you how to take the union. But if you have direct sums, I can always sort of include X, into, what I might write as X plus 1, right? Where 1 is the identity for the, so I apologize, I don't really mean direct sum here, right? I mean the symmetric monoidal product. Although for the example of modules, of course, you can think of the direct sum. But, what does that mean? Well, if I had an automorphism of X, that's X, and that's, the identity, right? And that's sort of more or less what we did in the case of this thing. And now think about the diagram you get there. Remember, every projective module, has the property, finitely generated, that, P plus some Q sits inside of an Rn. And so more generally, I guess here I can extend from P into, maybe say something more general. If I have P and I have an automorphism, I can put that inside an automorphism of P plus Q, which is P and the identity. And now if you think about the diagram I get, I can take a colimit over these automorphism groups over this diagram. And what this tells you is that the projectives always eventually sit inside some automorphism of a free module. Now, if I was being precise about this, I would talk about the theory of cofinality for colimits, right? That's what this is. And just to say a word about, actually, maybe I should pause for a second. Raise your hand if you know what cofinality means. Okay, that's a small number of people. That's fine. So here's a very natural question. Actually, let me ask a different question. Raise your hand if you know what a colimit is. Okay, great. So if I have, so here's a question I can ask. Supposing I have a diagram D going to some category C I care about. Okay, so you should think of D, I mean, you can think of D however you want, but a nice way to think of D is some small discrete category, right? Like, I don't know, D is equal, for instance, to, say, that category, which is the kind of colimit I was writing up above. You can ask if I have D prime contained in D. I mean, you can ask this very generally, but let's take the case of I have D prime contained in D. So this restricts, I get a functor from D prime to C. And now I can ask, when is the colimit over D? Oh, I guess I need to write these functors. Let's call this F, and let's call this F bar. When is the colimit over D of F isomorphic to the colimit over D of F bar? And that's supposed to be a question. So, right, and this is a natural question because you want to ask, when can I simplify my diagram? And what it means to be cofinal is precisely a condition under which this is true. And cofinal means that for everybody, so we say this is true when D prime is cofinal in D, and more or less what the sort of example you should keep in mind for that is precisely the example of the diagram of free and projectives. Namely, everything in here, D prime is in the case of the diagrams of free and projectives that we're dealing with, you should think of D as projectives, or isomorphism classes of projectives indexed, and D prime is the frees. And the point is that every projective eventually sits inside a free. And so, sort of if every object of D maps into D prime, into some object in D prime. So let me put this in quotes because I'm not setting up enough machinery to make a precise statement here. But anyway, so the point is that K1 does not see the difference between proj R and free R because the frees are cofinal in the projectives. Yeah? Yeah, I probably do. I think that's right. So I apologize because I don't want to take the time to do this category theory carefully, mostly because we don't need it. This is not authoritative. I mean, maybe it's authoritative, but this is not a careful discussion of what you really need for the theory of cofinality. What I should leave you with from this, so what should you get from this sort of vague thing I said? The slogan is, it's an interesting question to ask when two diagrams have the same colimit. It's an interesting question to ask when two diagrams have the same homotopy colimit, right? You saw homotopy colimits and homotopy limits yesterday, simplifying the diagrams you work over while getting a weakly equivalent homotopy limit or colimit is an extremely important question. And there's a notion of homotopy cofinality, as you might expect in that context. Okay. So, good. Let me say, what did I want to do? I wanted to do lots of stuff, but I think I'm only going to do a small piece of it in the remaining time. So, let me leave you with a discussion of what K1 is, and maybe a whisper of an application. So, what do you notice about K1 from these sorts of descriptions? So we know that the units, now here R once again is a ring, the units map into K1 of R, right? Every invertible object in R is a 1-by-1 matrix, which lives in GL1, right? So there's an obvious map like this, but we have a map this way, right, which is the determinant of a matrix. And this is clearly a splitting, right? And so, as a consequence, K1 of R is isomorphic to the units of R, plus something else, often which sort of unhelpfully gets written as SK1 of R. But, you can make whatever notation you want, I guess. But the point is that, so this encodes, if you have a ring, a very natural kind of thing, if you have a number field or something like that, if K0 tells us about the ideal class group, K1 tells us about the units. And we won't really talk about this, but K2 tells you about the Brouwer group. And there is a K2, although, well, we'll see what we say about that. So this is thing 1. And thing 2 about K1, I want to maybe very quickly talk about the significance of, so now I want to talk about the significance. So I gave this dichotomy in terms of the algebraic number theory applications of this stuff, where you put in something like a Dedekind domain or a number field, and talk about the geometry where you put in z pi 1, right? So let's do that here. So significance of K1 of z pi 1 of x, right? And this is going to be related, once again, to manifold geometry, and in particular, this is related to the S cobordism theorem. Okay, so let me say a little bit about the question that this is resolving. So again, what's the story? I'm going to produce an obstruction that lives, or I won't even produce, but I will explain a little bit about an obstruction that lives in K1 of z pi 1 m. And the question is the following. Suppose what am I going to suppose? So suppose I need a good name for a cobordism, which is not C. I don't know. Let's say that A is a cobordism between M and N. So, the boundary of A is equal to M union N. And I'm going to further assume the following thing, that M into A and N into A, that these are weak equivalences. These are homotopy equivalences. Now, you know an example of such a cobordism, namely the cylinder. Right? If you take the cylinder, if A is equal to M cross I, and M and N are equal to both to M, then that's an example of this phenomenon. And so a very interesting question you might ask is, are there examples which are not the cylinder? Right? If you think about it, that seems bizarre. Or that maybe depends on who you are. I find that question bizarre. It's not easy to come up with, or it's a good question, but the idea that there could be things that are not the cylinder is strange, right? So let me write that question down. So clearly, example is A equals M cross I. Now, question are all. So this data is called an H cobordism, by the way. Now the question is, are all examples the cylinder? And if these things are simply connected, then the answer is yes. But if they're not simply connected, then there's an obstruction. So if M is simply connected, then yes. Otherwise, there's an obstruction, which we'll call tau, which lives in, as you might hope, K1 of pi 1 on M, and I'm going to quotient out by plus or minus M. Okay, so each of these things act as an automorphism. Sorry, that doesn't make any sense, but quotient out by plus or minus pi 1 of M. Right, these things act as automorphisms. These elements, the elements of the group. Goodness, let's try to write this correctly. Okay, sorry, it's the group ring on the fundamental group. Elements of the fundamental group and their negatives act as automorphisms, and so they sit in there. It makes sense to quotient out by them. And there's a class tau such that tau is 0 if and only if this thing is a cylinder. So tau, this is called the Whitehead obstruction. This is the Whitehead group. Tau is 0 if and only if answer is yes. Now, how do you produce tau? You end up producing a matrix. And where this matrix comes from is that, and I'll do this construction, I think, at the beginning of the next lecture. If you have a quasi-isomorphism between complexes, and you look at the mapping cone, then there's a matrix that gives an isomorphism between the even and the odd parts. And for a suitable complex, that matrix, regarded as a K1 class, is this Whitehead thing. Okay? But again, the point of this example is that if you are interested in questions in manifold geometry, you can often reduce these obstructions to what seem like completely unrelated questions, to questions about the behavior of algebraic K-theory groups. And this study of the sort of the Whitehead group is actually very rich. Right? I could give a long lecture series on the interesting applications of this. So, for instance, you can I think Smale used this to prove the sort of high-dimensional PL Poincare conjecture using computations involving the Whitehead group. Or actually, I don't know how Smale proved it, but we can now interpret what Smale did in terms of the Whitehead group. And there are a bunch of other interesting geometric applications of this. So, and that probably is a fine place to stop for lunch. So let me tell you so two things to say. So what did we do, right? What's the take-home lesson from today, which was that just as there's a K0, there's a K1 which somehow generalizes K0. And actually, let me say one more thing before I release you to food. So, because I don't want to say, or I'd like to say this now, and let me make sure I write this properly. Well, actually, maybe I'll write this again next time. But one thing you might wonder is, why are we talking about, why are we naming this K1? Right? I mean, normally when you call things 0 and 1, you might expect for there to be exact sequences connecting them. Right? That's what your experience in topology might want to tell you. And indeed, if we have, it's a theorem, I think maybe due to Bass, that if we have R1, R2, R3, and R4, and this is a Cartesian, this is a pullback square of rings, and I'm going to assume that this map F is surjective, then there's a Meyer-Vietoris sequence in the K groups. Right? We have Meyer-Vietoris connecting K1 of R1 to K1 of R2 plus K1 of R3 to K0 of R4, and so on. And I'll write this out and some other exact sequences more carefully next time, and explain something about what these maps are. But the point is that there are long exact sequences connecting K0 and K1. So I motivated this from the perspective that, gee, I want to study module categories, and so studying first isomorphism classes and then automorphisms of objects is sort of the thing as mathematicians that you do, right? That was the pitch. And that's a good pitch. But there's another way to think about this, which is that you want this to be an analog of what you see in topological K-theory. And in topological K-theory, that's a cohomology theory. And of course you have things like a Meyer-Vietoris sequence. And so you want to build your K1 such that that's true. And Bass's insight, Hyman Bass is the person who invented most of the theory of K0 and K1. Well, maybe invented is wrong, did an enormous amount of work on it, like Grothendieck invented K0. But one of the things he established was that indeed there's Meyer-Vietoris like this, and you can even extend this down to the right with negative K groups, about which we'll say nothing further. And then the motivating problem was, can I extend it to the left? And the answer is sort of. And or the answer is it's complicated. And so, but we'll do that, kind of. So in terms of where we're going, so we've seen K0 and K1 as explicit constructions and things that you can build, and as exercises you should calculate for your favorite rings. Try to figure out what these are. And we're now going to shift to talking about homotopy theory and sort of higher algebraic K theory, and things are going to get different in character. But I guess we'll see that next time. So now I really am done. I like how there's this sense that you should clap quickly before I continue to say things and possibly prolong. Anyway, any questions?